We are Team R10 presenting our design for a satellite launch system for our AAE 251 Introduction to Aerospace Design course. Our team is composed of Robert Jezior, Noah Gordon, Lucas Moyer, and Mario Robledo.
We began this project by asking ourselves, what is so enticing about life beyond low Earth orbit? Rather than picking a planet like most prospective missions are all about, we thought it would be interesting to get to explore asteroids instead. We wanted to explore the environment anywhere near an asteroid's orbit. In order for our mission to be successful, we had to design a rocket that met and exceeded the requirements desired by our stakeholders. This rocket had to be capable of escaping Earth's orbit and transfer our satellite safely into orbit around Purdue 323. Once in orbit, our satellite would then use its instruments to collect data from any space debris coming from or near the asteroid, analyze and process this data, and transmit it back to headquarters.
We began our design by determining the stakeholders of our project and determining what they need to be satisfied with the final design. We determined that the most important stakeholders for our design are NASA, specifically the astronauts whose lives depend on the data collected by the satellite, and also the taxpayers who will fund the satellite's development. These stakeholders require our satellite to be cheap, cost-effective, yield accurate data, and have the ability to send that data back to Earth within 48 hours. Our system requires a total delta V of 14.325 kilometers per second, approximately 7.8 to get into low Earth orbit, and then the rest to get to our desired destination, which is to achieve orbit around the asteroid 323 Purdue.
Sending a satellite into orbit is an inherently risky task. The largest risk we had to mitigate in our design was the risk of a catastrophic failure during launch, resulting in the complete loss of our system. Even when catastrophic launch failures are avoided, the risk remains of significant damage to our satellite due to the vibrations caused during the launch process. Some other risks that we considered include our satellite losing power due to a solar panel malfunction, or our satellite colliding with space debris. We consider these risks to be very low because they have a low probability of occurring.
In order to make our decision on our final design, the first thing we did was to conduct background research on our required delta V, past vehicle comparisons, and propellants. After finding data on delta V calculations to asteroids that were roughly the same distance as ours, we were able to verify that our delta V calculation is reasonably accurate. Looking at past vehicles for similar missions, we were able to get a rough idea of what kind of system we would have to design to complete our mission. After researching various propellants, we narrowed down our choices to ones that have been commonly used in the past and will give us the lowest initial mass for our rocket.
To calculate the required delta V for the mission to 323 Purdue, we broke it into 4 parts. First, launching into a parking orbit 200 kilometers above Earth's surface. Second, changing inclination to the inclination of the asteroid because the latitude of Cape Kennedy, our launch site, is greater than the inclination of the asteroid, assuming that the equatorial planes for the Earth and the Sun are coplanar. Third, entering the home and transfer orbit, and lastly, transferring to 323 Purdue's orbit from the transfer orbit. The sum of the required delta V for each of these parts of the mission gave us a total delta V of about 14.3 kilometers per second. We also had to calculate the optimal delta V fractions for our staged launch vehicle. We wrote MATLAB codes to optimize the delta V fractions for a given payload mass, inert mass fractions, and ISPs. The programs also calculate the necessary initial mass of the launch vehicle and return required propellant and inert masses for each stage. We use these codes to run multiple different scenarios for both 2 and 3 stage rockets with different propellant combinations and mass fractions to decide on our final design and to size the launch vehicle. We are creating a mini satellite system modeled after the ESA's Proba family using many of the same instruments. Using Proba 1 specifications, we arrived at an estimated payload mass of 140 kilograms. We are planning on using our satellite to analyze the 323 Purdue asteroid. In order to get our satellite system to the asteroid, we will be using a 3-stage rocket with all 3 stages powered by a liquid hydrogen and liquid oxygen bipropellant. We arrived at this launch vehicle design after considering many different propellant combinations and stages. We decided the trade-off of lower density for lower initial mass and higher ISP was worth it since our rocket would still not be an unmanageable size, such as in the case of Saturn V. Our initial mass is calculated at 9,767 kilograms for this design. Using a solid propellant for the first stage, even if it cut the inert mass fraction for that stage in half, resulted in a mass over 13,000 kilograms, and an equivalent 2-stage rocket would be almost 24,000 kilograms.
Throughout this project, we learned a variety of lessons about the design of aerospace systems. Through all these lessons, we as a team learned that aerospace systems design is so much more than simply creating an aerospace vehicle. The design of aerospace systems is an art that requires analysis of who will be affected by the design's success or failure, comparison of all possible solutions, and a design decision justified by neutral metrics. Put together, these analyses must be used to make intelligent design decisions that lead to the best possible product.
The first lesson we learned was how to refine our needs and requirements definitions, having initially wrote needs and requirements that were much too vague. It is important that our needs and requirements are specific so that our goals were clear and so that anyone reading our project proposal could get a much better understanding of our goals.
Another lesson we learned after completing this project is why it takes so many people to design aerospace systems. Even though our project and design is relatively simple and makes lots of assumptions compared to a real-life system, we still had to distribute all the work and delegate tasks while maintaining an understanding of the entire system and how each of the subsystems contribute to the functionality of the system.